constraints essentially by pulling those in from the kinematic simulation that we just saw. The next thing I want to do is identify the parameter that I want to drive in this simulation. And it's just going to be the thickness of that first extrusion. And as it happens, I've set up the thickness of this beam to match the thickness across the part. So we're actually going to drive those two together, and we're going to look for a value that matches up with our objective design criteria. So to do that, I'm going to click on the parametric table here, and you'll notice that that thickness parameter has already been brought in. I'm also going to add some design constraints here. I'm going to say I want to look at the mass of this part, and we're going to, instead of just viewing the value here, what we want is the minimum mass. And we can also add other design constraints. So we don't just want this part to be as light as possible. We also want to be able to go in and say, for instance, I don't want the equivalent strain in this part to exceed an upper limit of, let's say, 1.5 thousandths of an inch. And so we've got these two criteria which obviously are kind of conflicting with each other, right? I mean, the lowest mass part is going to have a little bit more strain in it, and that basically what we're looking for is a design configuration that allows us to achieve both of these goals at once. We want low mass, but we also want to make sure that we don't get too much strain in that part and actually start to, you know, mess up our kinematics potentially if this thing became too flexible. But we'll go ahead and input some values here that we want to examine, and I'm just going to kind of scatter across 3, 5, and 10 millimeters there to begin with, and that's going to actually change the thickness of that extrusion to those values as I go along. So we continue moving to the right here. We could assign a material. You'll notice that this part has actually been assigned to stainless steel. We'll use the as defined option here. We could go in and create an override here real easily if we wanted to say try this out with titanium as well. We could do that real quickly without actually going back and modifying the model or changing our bill of materials or anything. Right here in the simulation environment, we could just override that and see what kind of results we got as a result of that. For now, we'll just leave that as modeled. And the next thing we want to do here, the forces and constraints, as we said, have already been pulled in, so we'll just move right on over to our mesh view here. And we're going to go ahead and create a mesh of this part. This is, of course, where finite element analysis gets its name. As you can see here, that part has been basically converted into a series of finite elements that are going to transmit the stress as basically spring and mass type of elements, and we have the option here to do various different things. We've got local mesh control. We could go in and adjust the mesh down on certain faces to get a more accurate representation of the stress in a certain region. We can also go in and set up a convergence. So, for instance, we could say I want to allow the mesh to be refined up to 3 times, and I want to stop refining the mesh in local areas if my results converge to within 10% of each other on any 2 iterations. So I'm going to go ahead and do that, and basically we're checking the von Mises stress to make sure that it is staying within 10% from one mesh iteration to the next as we go through this process. And at the end, we can take a look as well and see how well those things converge between the various different iterations there. So I'm just going ahead and letting this simulation run here. It's going to take a couple of minutes for the computer to go through and solve all of the different combinations that we've given it. We've given it 3 different versions of the geometry, as well as potentially 3 different refinements on that mesh. And as you can see, it cranks through those pretty quickly. And we've got, as a result here, kind of an overly exaggerated version of the deflection. You'll notice over here under display we can see the actual deflection if we wanted to look at that, and of course as we can see here with a steel part we're not expecting a whole lot of deflection, and indeed there isn't much. But the scaled options here are really nice for being able to really see what the mode of that deflection really looks like and what that effect is. Obviously much exaggerated, so that you can really see it with the naked eye. But we'll go ahead and drop this back to scaled there. And also over here in our parametric table, we've, looks like my options didn't take there, so I'm going to go ahead and add those back in real quick. And we'll just run that guy one more time. There we go. And that's going to go through and catch all three of the variations that I had just created on that part. So initially we're looking at a 10 millimeter thick beam coming off of both sides of that rocker arm, and of course, you know, that's probably kind of thick for what we're doing, right? It's only we're only driving a force of something like 75 newtons or something like that. We maybe don't need to go quite that thick, so we're going to find that out here real quickly as to how that looks in the other two thicknesses with respect to our allowable equivalent strain. So initially our results are showing our von Mises stress. Notice we can also click through and look at the displacement on the parts. We can see how far those moved. We can look at this at the factor of safety on there. The factor of safety is the only one of these that is not necessarily going to show red. This one scales from blue to red, going from a factor of safety of 15 down to 0. And of course we want to keep that somewhere up above 1 in order to make sure that the part isn't yielding. We can also have a look at our convergence plot here, and as we notice here, this ran 5 different steps for convergence. Between the last 2 steps, the difference was only 3%, so it went ahead and stopped there. That convergence plot is obviously very helpful in being able to know that the mesh that we wound up with as our end result mesh was in fact accurate, and churning out accurate results that aren't, you know, overly affected by the fact that these elements are of course finite. They are not infinitesimal in size, and sometimes if they're too big you can work your way into some error there, but here we can be reasonably confident that that error is somewhere on the order of 3 to 5% or so. So let's take a look at our parametric table here one more time, and you'll notice when we slide that slider bar, we're going to change the result set over from the 10 millimeter version down to the 5 millimeter version, and then we can drop this down into the 3 millimeter version as well. And as we can see here, we're getting progressively more stress on each one of those. If we click over to safety factor here, you notice we're still achieving a good safety factor in that region, but the von Mises stress is certainly turning up, and the total displacement, we're actually winding up with 30 thousandths of an inch of displacement from the initial location on that one value. And in fact, we could go in and modify that and add a displacement tracker, so to speak, here. And in fact, I want to look at the Y displacement on this